So, back in 2017, a group of 8 researchers from Google published a paper, and its title was deceptively simple. Attention is all you need. They probably couldn't have known it then, but this paper, it wasn't just going to improve AI. It was going to completely rewrite the rules and pretty much kickstart the entire generative AI revolution that we're living in right now. So, let's dive in.
To really get why this paper was such a big deal, you have to start with a really basic question. How does a machine, a computer, actually read a sentence? How does it figure out the connections between words, the grammar, and what it all really means? For the longest time, the best AI models did it pretty much the same way we do. They'd read the first word, then the second, then the third, and so on, right down the line. But here's the thing. That approach, while it sounds logical, was actually creating a massive fundamental problem that was holding the entire field back.
And that brings us to what's known as the sequential processing problem. You can think of it as this giant bottleneck that basically put a hard limit on what AI could do with language.
See, at the time, the top-tier models were called Recurrent Neural Networks, or RNNs, and they had some really serious drawbacks. Because they had to go word by word, you couldn't throw a ton of computer power at them in parallel to speed things up. And maybe even worse, if you gave it a long paragraph, by the time the model got to the end, it had often forgotten what was said at the beginning. Not great. Now this is where you get that big aha moment. This table comes straight from the paper. For those RNNs, the number of steps it has to take grows with the length of the sentence. That's what the O of N means. But look at self-attention, the new kid on the block. It's O of 1, a constant number. It literally doesn't matter if the sentence is 10 words long or 10,000. It takes the same amount of time. That was the key that unlocked massive parallel computing.
So what was the solution? Well, the authors didn't just try to improve the old method. They decided to throw it out completely and replace it with something revolutionary, an idea called attention.
I mean, just listen to this quote from the abstract. It's so bold. They're proposing a brand new architecture, the transformer, based solely on attention. They completely got rid of the one-word-at-a-time processing that had been the standard for years. This was just a totally radical idea.
So what is this magic trick? The paper calls it self-attention, and in simple terms, it's a way for the model to look at all the words in a sentence at the exact same time, and for each word, it figures out which other words are the most important for understanding it. This totally solves that memory problem, right? Every word can now connect with every other word, no matter how far apart they are.
A really great way to get your head around this is the librarian analogy. So for every single word, the model generates a query, which is like a specific question. Then it compares that query to a set of keys. Think of these like the labels on all the books in the library. And based on how well the question matches the labels, it pulls out a very specific blend of values, the actual information inside the books, to create the perfect, context-rich meaning for that original word.
And this is how they took that core idea and made it incredibly powerful. The mechanism on the left, that's the core engine. But the authors figured, hey, one perspective is never enough. So they basically built the V8 engine you see on the right, multi-head attention. It runs a bunch of these attention heads all at the same time, in parallel. Each one is kind of looking for something different. One head might be tracking grammar, another might be tracking who did what to whom. Altogether, they create this incredibly rich, multi-layered understanding of the text.
Okay, so we've got these super powerful attention engines, but how do you actually assemble them into one working model? Well, let's take a look at the architecture itself.
And this is it. This is the famous diagram from the paper showing the full transformer. I know it looks a bit complex, but it's actually incredibly elegant. At its core, it's really just two main parts. You've got an encoder on the left and a decoder on the right.
Right, so think of it as a two-part team. The encoder's job, over on the left, is to read the entire input sentence, let's say it's in English, and build a super detailed numerical representation of what it means. Then, the decoder, on the right, takes that understanding and uses it to generate the output sentence, maybe in German, one word at a time. And here's the beautiful part. At every single step of its process, the decoder is paying attention to the entire input sentence to make sure the translation is spot on and makes sense from start to finish.
So the theory was brilliant. The design was elegant. It was a totally new way of thinking. But in science, a cool theory doesn't mean much without results. So the big question was, could it actually beat the competition?
And really, this was the billion-dollar question. Could a model that completely ignored the idea of sequential processing actually understand language better than the models that were designed for exactly that purpose? The answer was a huge, unmistakable yes. This table from the paper shows the scores on a standard translation test. The best models before this, even when you bundled a bunch of them together, got a score of 26.36. The big transformer model, it hit 28.4. It didn't just squeak by, it set a brand new state-of-the-art.
Now, a 2-point jump might not sound like that much, but trust me, in the world of machine translation, a jump this big on a major benchmark isn't just a step forward, it's a massive leap. It's the kind of result that makes the entire research community just stop what they're doing and pay attention. But believe it or not, the performance wasn't even the whole story.
And here's the real kicker. It wasn't just better, it was so much more efficient. Because it was designed for parallel processing, the transformer got these amazing results using, and I'm quoting here, a small fraction of the training costs of the best models from the literature. Better, faster, and cheaper. That's like the holy trinity of any engineering breakthrough.
So, you see, this wasn't just about building a better translation model. This was a whole new blueprint for how to build AI that can understand complex patterns and data. And its impact, well, it's been absolutely staggering.
So why does some academic paper from 2017 matter so much to you today? Well, because the transformer architecture is the foundation, the literal bedrock for almost all the modern AI you interact with. Every time you use a large language model, or a chatbot like ChatGPT, or an AI image generator, you are using a direct descendant of the ideas from this one paper.
It's kind of funny to read the last sentence of the paper now. The authors said they were excited about the future and planned to apply these models to other tasks. Talk about a massive understatement. It's safe to say that vision came true on a scale that maybe even they couldn't have imagined. In the end, attention is all you need proved that if you let a model look at everything all at once, if you let it weigh the importance of every piece of data against every other piece, you could unlock a level of understanding nobody thought was possible. It was a true paradigm shift. And it leaves us with this huge question. What's the next bottleneck to break? What's going to be the next attention?